In the world of automation, you've got two kinds of machines. Some are built to run forever, day in and day out. But others, they have a specific mission to complete. Today, we're going to dive into the powerful logic behind those mission-driven systems, a way of thinking that gives machines a clear, crucial finish line.
So let's think about this for a second. On one hand, you've got a web server. Its whole job is just to run, indefinitely, forever. But then you have a delivery drone. It has one very specific, very finite mission. Get from point A to point B, and then it's done. Programming for a task with a clear endpoint like that, well, it requires a totally different kind of logic, a whole new instruction manual for the machine.
All right, so here's our game plan. First, we'll look at why programming for forever can actually be a trap. Then we'll meet the logic that's built for that finish line and unpack its superpower, something called synthesis. We'll also see how it handles real-world chaos, why having an end is actually way more efficient, and what this all means for the future of automation.
So let's start with the problem with forever. See, a lot of traditional logic for systems was designed for those infinite tasks like that web server we mentioned. But when you try to apply that same logic to a finite mission, it's like using a sledgehammer to crack a nut. It's not just overkill, the complexity can actually get in the way of the mission succeeding at all.
And this is exactly where a new kind of logic comes into play. One designed from the ground up for these finite missions. It's not about building a perpetual motion machine. It's about getting a job done and getting it done right.
It's called LTLf.
Yeah, I know, it's a mouthful. It stands for Linear Temporal Logic over Finite Traces. But put simply, it's just a really precise language for giving instructions to systems that have a clear beginning and, most importantly, a clear end. That linear temporal part, it just means it thinks about time as a straight line of events, one thing happening after another until the mission is complete. Simple as that.
And this analogy on the slide it puts it perfectly. Traditional logic is like trying to build a perpetual motion machine, this incredibly complex, maybe even impossible task. But LTLf, that's like programming a self-driving car for a very specific trip. We're not trying to solve for infinity here, we're just programming a clear, defined journey from A to B.
So what makes LTLf so powerful? What's the secret sauce? Well, it all comes down to one core concept: synthesis.
Synthesis is pretty much magic. It's the process of automatically creating a working system just by describing its goal. So instead of a programmer having to write every single line of code, you just provide the high-level objective. Synthesis then does the heavy lifting and generates the detailed step-by-step instructions. It turns the what you want into the how to do it.
This slide shows the process beautifully. First, you just describe the goal in LTLf, a simple human-readable instruction like, get coffee, and oh yeah, avoid obstacles. Then, the synthesis engine takes that goal and thinks through all the possible actions and scenarios. And finally, boom, it spits out a complete program, a detailed controller that knows exactly how to pull off the mission.
Okay, so how does this actually apply in the real, messy world? Well, that focus on finite tasks is exactly what lets LTF tackle these incredibly complicated problems, the kind that become almost impossible when you're trying to solve for infinity.
For example, we all know the real world is unpredictable. What if our delivery drone's camera suddenly gets foggy? Well, LTL synthesis can handle this. It's called partial observationality. It basically allows systems to make smart, strategic decisions even when they can't see the full picture.
But it gets even better. It's not just about getting the job done. It's about getting it done optimally. And this is where something called quantitative synthesis comes in. LTAFF can find the most efficient strategy, not just any path for the drone, but the absolute fastest path, or maybe the one that uses the least amount of battery.
And of course, these systems have to follow the rules, right? You can build an LTLf framework with core assumptions baked right in, these non-negotiable principles like fairness or stability. Think of them like the traffic laws for our drone. It knows its destination, but it also knows it has to obey the rules of the road to get there safely.
Now, this focus on finite tasks has another massive, though maybe less obvious, advantage. It makes the entire system way easier to verify and check for errors.
Just look at this table. This is where it gets really interesting. Look at the verification complexity. For a finite system, one that ends, the difficulty is PS space. Now, that's complex, sure, but it's computationally manageable. But for an infinite system, it jumps to EXPS space. That is not just a little step up, it is an exponential leap in difficulty. It makes it practically impossible to prove the system is correct in a lot of cases. It's just fundamentally harder to prove something will work right forever.
So the takeaway here is simple, but it's really profound.
By designing systems for finite tasks, we make it practically possible to prove that they're safe, that they're correct, and that they're reliable. It's just smarter engineering to build something you can actually guarantee works the way you intended.
So, where is all of this heading? Where is this powerful combo of finite logic and automated synthesis making a real impact right now?
Well, LTLf is already a total game changer in a bunch of advanced fields. In AI, it's a bedrock for strategic planning. In robotics, it's being used for motion and task planning, guiding a robot arm to assemble a product. It's even used to model complex business workflows. In all these areas, it's the critical tool for making sure these complex systems actually work.
And that leaves us with a really fascinating thought to end on. We are building the ability to automatically generate incredibly complex programs just by describing a high-level goal. So as this technology gets better and better, you just have to wonder, what complex jobs are going to be automated next?